Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we are going to show that the conditions of the integral test fail to apply to given infinite series. So for that reason, the integral test won't be applicable to determine the convergence or divergence behavior of the series. So that means in the conclusion, if you cannot apply the integral test to the given series, so that means you have to rely on two other tests. We're not going to discuss about it, but this could be like a good exercise for you in the long run. That hey, we can't apply the integral test to the given infinite series, so why don't we apply the other tests like ratio test or root test or some other tests available so that you can say something about the convergency behavior of the infinite series. All right, we have two exercises to go. Let's get started. All right, so let's check what the conditions of the integral test are. So we had three of them, in fact. One is f being positive, 2 is f being continuous, and 3 f being decreasing. Apparently one of those conditions, or maybe more than one of those conditions, fail to hold true for the given infinite series. So we're going to sort of like pinpoint which condition fails. If you find one condition failing, then it's enough to conclude that integral test is not applicable for the given infinite series. All right, for part A, why don't we construct an equals fn, that's equal to e to the minus n cosine n, that allows us to grab f of x to be e to the minus x cosine x. Okay. So the very first condition was checking for f being positive. Okay. That's one thing that you may remember from pre-calculus or calculus, that cosine is a fluctuating function in between -1 and 1. So cosine, in fact, may take negative values depending on which x you're talking about. And in this case, x is greater than or equal to 1 because n starts from 1 here. Okay, so so that makes you think that f may not be positive, and in fact, if you look at f of 3, e to the minus 3 cosine 3, this is negative. All right, so the problem here is not the exponential part of this product, it's the cosine, right? Cosine 3 is negative, so this makes this function negative. And you can also check cosine 8, so you can look at f of 8. So it's always, it's just negative. So since cosine is a periodic function, so you're gonna, like, as you increase x, you're gonna find x's for which f is negative. So the first condition of the integral test fails, so we can't say f is positive anymore, right? So that condition fails to hold true, so that means I cannot apply the integral test for the given infinite series. Okay. All right, let's look at part B. So I'm going to grab, as always, I'm going to grab an equals fn. I'm going to sort of like grab the function f in terms of x. Okay. Three conditions to check. One is f being positive. So let's check. Well, sine, well, this is a quotient to start with, and plus x is greater than or equal to 1. So sine x over x, as long as x is not equal to 0, which is the case here, because x's are chosen to be greater than or equal to 1, we're safe, and now we're taking the square of the quotient, it's always positive. So put a check mark here. Number 2, continuous, right? Well, let's check f is continuous. Okay. Sine is a continuous function, no problem. X is a polynomial, which is a continuous function. Sine x over x is continuous as long as x is not equal to 0, because for x equals 0, you have sine 0 over 0, which is not defined, right? So, but we're safe. X is greater than or equal to 1, so I can go ahead and say that f is the quotient of two continuous functions, so it's continuous, okay? And in fact, taking the square of that doesn't change anything, right? Any power of a continuous function is a small continuous. That follows from Calc 1, okay? So the next condition is f decreasing. Is f decreasing, right? So to sort of answer that question, remember that we rely on to f prime. So we need to find f prime, okay? So why don't we use the chain rule to take the derivative of this function, because this is the inner function sine x over x, the outer function is taking the square, so we can use the chain rule. So so you put the 2 down, 2 times the inner function times the derivative of the inner function, right? Okay, so let me just quickly go through that calculation here, because I need to use the quotient rule to take the derivative of sine x. So what is it? So the derivative of the top times the bottom minus, I don't like writing like cosine x times x, but we generally put x in front of cosine so that we don't really mix those x's. Okay, so x cosine x minus, keep the top, take the derivative of x. Well, that's sine x, all divided by x squared. Okay. All right, for this function, you are checking the sign of this function here. I mean, it's not easy to see that this function is negative or positive. I think at this moment, it's the best for you to pause the video and plot this function for x min, let's say, starting from 1. Use your TI-84, plot this function, and you will see that this function is not negative. Because, as I said, we have periodic functions, sine and cosine, and their composition. So this should be taking positive and negative values. So I can't conclude that this is less than 0. Okay, so I cannot do that. Okay, so again, to verify this, it's hard to see. You can also plug in some numbers for x and check for which x this is not negative, but it's the best to plot this function and see, like, you have some part of the graph being about the x-axis and some part being below the x-axis. So here the third condition fails, so I have this condition failing. So this simply means that I cannot use the integral test to prove convergence or divergency. So integral test is not applicable. Okay, so does that mean that I cannot prove that the series is not convergent or divergent? No, because I can use another test. We have a bunch of tests available for checking the convergency, divergency. So then you're going to rely on to another test. For these two examples, again, the integral test is not applicable because in one case the first condition fails, in the second case the third condition fails. So integral test is not applicable. Okay, check for other tests, other applicable tests to verify the convergency or divergency of these infinite series. All right, so I think that's the end of the video. Thanks for watching. I'll see you in another video. Bye.